Hello, everyone. Hope everyone is well. So, today I wanted to think about this problem, which is if you have a triangle, ABC, and you put a point X inside this triangle, what is the largest possible value that AX plus BX plus CX can take? So that is the problem we will be thinking about. And just so you know, this is a very old problem. It's probably thousands and thousands of years old. Hello, Ken. How are you? So, as I was saying, this is a very old problem. I think it belongs to the Greeks. It's extremely old. And of course, there's like a classical solution and kind of a modern solution to this problem. And we're probably going to talk about both. Please let me know if you can hear me and if the music is, not too loud, etc. And if not, let's get going. So let's think about this value AX plus BX plus CX. All right. So let's try to examine this value and see what we can say about it initially. Okay. So if we're examining this value, the first thing to note is that let's try and start with the following. So AX plus BX plus CX is going to be less than or equal to the perimeter of this triangle. And it's going to be greater than or equal to the perimeter over 2. Okay. Let's try and examine this to start with. Okay. So, in fact, the following is true. AX plus BX plus CX is greater than or equal to the semi-perimeter, and it's less than the perimeter of this triangle. And remember, X can take any position in the interior of the triangle or on the boundary of the triangle. Okay? So now, let's start by proving this first part. So we'll start by showing that AX plus BX plus CX is at least as large as the semi-perimeter of this triangle. Okay? So why is this? What's going on here? This one turns out to be fairly easy to prove. And we'll just do this one as kind of like a warm-up to of things to come. So let's start with there. Let's prove that no matter where X is on the interior or on the boundary of the triangle, we want to show that AX plus BX plus CX is greater than or equal to the perimeter divided by 2. Well, if you think about it, this triangle, inside of it, there are 3 triangles. Let me just put this over here. You can immediately notice from here, of course, that, AX, so ACX is a triangle, right? BCX is a triangle, and ABX is also a triangle, okay? So now, that means that, of course, let's see. So starting out, you can apply the triangle inequality to all 3 of these triangles on the inside, right? And so you immediately get, of course, that AC is going to be less than or equal to AX plus XC. And of course, this comes from applying the triangle inequality to this triangle. Okay? Similarly, BC is going to be less than or equal to, BX plus XC. Okay? And applying the triangle inequality to this triangle is going to give you that AB is less than or equal to AX plus XB. Okay? Adding all these up gives you, of course, if you add all these up, you get AB plus BC plus AC is less than or equal to 2AX plus 2XC plus 2XB, right? Dividing both sides by 2 gives you that, AX plus XC plus XB is greater than or equal to the perimeter divided by 2. Okay? So that's just a little warm-up for things to come. We're going to be doing a lot of arguments in this style today. But rest assured, there's a deeper, perhaps very interesting fact hidden inside this problem. Okay. So what we've managed to figure out is that no matter where x is on the interior or on the boundary of the triangle, we've managed to figure out that ax plus bx plus cx is greater than or equal to the perimeter divided by 2. The other side of this turns out to be slightly more challenging. So how do you figure out that ax plus bx plus cx is less than or equal to the perimeter? So, let's see here. How might one even begin to try and figure out that ax plus bx plus cx is less than or equal to the perimeter of this triangle? By the way, I'm not saying that the perimeter is the maximum value for ax plus bx plus cx. All I'm saying is that it gives you an upper bound. In fact, this is absolutely not strict. So the best you can say here is that this is definitely going to be less than the perimeter. We're going to come up with a tighter upper bound for ax plus bx plus cx. Okay? But this is not a bad place to start. It is a little bit challenging to figure out why ax plus bx plus cx is less than the perimeter. So let's get started. So how might we do this? I'm going to make a claim here. Hopefully it seems reasonable to you. If you take a triangle, you know, ABC, and you put a point X inside the triangle somewhere, the first claim that I'm going to make here is that AX plus XB is going to be less than or equal to AC plus BC. Okay? This might seem completely obvious. You know, you have a point X somewhere in the interior or on the boundary of the triangle. Then you should have that AX plus XB is less than or equal to AC plus BC. And of course, we're going to use this to prove the claim about the perimeter over here. Okay? How are we going to do this? This seems fairly intuitive. This seems a lot more intuitive than the original question. How can we possibly figure this particular thing out? Well, I said the triangle inequality would play a big role in all our machinations today. So there's a very clever ancient kind of proof to this. So let's talk about it. Okay? So we're trying to prove, of course, that AX plus BX is less than or equal to AC plus BC. Once again, AX is here, BX is here, is going to be less than or equal to AC plus BC. And all of our arguments that we make here should apply in general, right? It should apply to any point X that's either in the interior or on the boundary of any triangle ABC. Okay. How might you prove this? Well, watch this. So what I'm going to do is I'm going to extend this line segment AX to the other side of this triangle BC. Okay. Like so. I'm going to call this point out here Y. Okay? So I've extended this segment AX to this other point on the side Y. All right? And now let's see what we get here. Well, I do know for a fact that BX is less than or equal to XY plus YB. And of course, this comes from applying the triangle inequality to this triangle, right? So I do know for a fact that BX is going to be less than or equal to sort of XY plus YB, okay? And like I said, this comes from applying the triangle inequality to the inside of this triangle over here, all right? Well, what can we do from here? of course, this tells me that, you know, plugging this into here, we get that, well, not really plugging, but using this, just adding ax to both sides, you get that ax plus bx is going to be less than or equal to ax plus xy plus yb. Okay? But notice that ax plus xy, this over here, is just ay. Okay? So ax plus xy is just ay. All right. So let's plug that in, see what happens. You get that ax plus bx is less than or equal to sort of ay plus yb. All right, hopefully that seems reasonable. But now ay plus yb, let's think about this. Of course, ay is going to be, well, ay is going to be less than or equal to ac plus cy, right? So this is now applying the triangle inequality to this triangle in the middle here. So this triangle. If you apply the triangle inequality to this triangle, you get that ay is less than or equal to ac plus cy. Now, if you put that in here, like if you plug this into here, what happens? You get that ax plus bx is going to be less than or equal to ac plus cy plus yb. But of course, cy plus yb is just bc. So that proves our desired claim over here, right? So AC plus BC here. So AX plus BX is going to be less than or equal to AC plus BC. Very interesting. So what we've managed to prove now is that basically AX plus BX is going to be less than or equal to AC plus BC. But of course, the same proof will apply to you know, when you work with any side of the triangle, right? So if AX plus BX is always going to be less than or equal to AC plus BC, then this tells you that BX plus CX is going to be less than or equal to AB plus AC, right? And if that's true, then you also immediately get that AX plus CX is going to be less than or equal to AB plus BC. Let's add all of these together, and you will get that 2 times AX plus BX plus CX is going to be less than or equal to 2 times AB plus BC plus CA. And canceling the 2's now gives you the answer. So AX plus BX plus CX less than or equal to AB plus BC plus CA. Interesting. So what we've managed to figure out after all of this effort, of course, is that AX plus BX plus CX is definitely going to equal, or it's not going to be any larger than the perimeter of the triangle. However, I claim that this is still not the upper bound here, okay? So, oh, well, sorry, this is an upper bound, but it's not a tight upper bound. You can do better than this. So what have we managed to figure out so far? That AX plus BX plus CX is less than or equal to the perimeter of this triangle. So after all that effort, this is what we've managed to figure out. But this is not a tight bound, okay? So actually, the tight bound comes from the following rather surprising theorem. So actually, AX plus BX, so the maximum value, I guess I'll reveal the answer at this point. So the maximum value of ax plus bx plus cx is always the sum of the larger two sides of the triangle. The sum of the larger two sides of the triangle. I wonder how many people will see this one coming, okay? But it is true that the maximum value of ax plus bx plus cx is the sum of the larger two sides of the triangle. This is the theorem that I would like to go over today. So this is the theorem that I would like to essentially prove to you today. And there's going to be two approaches to proving this. I'm going to take a classical approach, and I'm going to take a modern approach as well. Okay. So I really like this proof. Yes, Ken. Right. Very good. Very good. So a classical approach will involve no kind of fancy machinery of any kind, right? But we're also going to, we're gonna present a proof that I actually think is very clever, not using anything more than triangle similarity and the triangle inequality. Okay, so how exactly is it that we are going to prove this? Well, let's think about it for a second. First things first, I'm going to use a particular fact about triangles. Okay, so for example, let's say I draw a triangle like so, and let's say this is A, B, C. Okay, I'm going to use the following fact. So let's say I have a line, a Chevian, in fact, that goes down from C to AB. So let's call this one X. Okay. Then CX is always going to be less than or equal to the larger of these two, the larger of, CA and CB. Okay. With equality only if X is equal to either A or B. This is a very kind of classic fact in geometry. If you want to see a proof of this, then notice that if you're drawing a triangle, right? If you, for example, take a circle of radius CX centered at C, right? Then one of A and B needs to be like they can't both be inside the triangle, right? So for example, if you draw a circle centered at CX, it is not possible that A and B both lie inside this circle and this still be a triangle. Well, I'll let you think about that, okay? But this is a basic fact from kind of classic geometry, right? So CX definitely has to be less than or equal to the larger of CA and CB, okay? So let's try and leverage this fact and kind of see what happens here, okay? So remembering this fact that if you draw a Chevian, it'll be less than or equal to the larger of the two sides that are on either side of it, okay? Okay. Now, let's see what we can do with the more general case using this fact. Okay, what can we do with the more general case using this fact? Okay, so this is A, B, C. And now we're going to try and prove that AX plus BX plus CX, its largest possible value is the sum of the two larger sides. Well, In order to do that, what I'm going to do is I'm going to just assume without loss of generality. Well, first of all, let me label the side lengths just so everything's a bit easier. So I'll call this a C, I'll call this A, and I'll call this a B, all lowercase, right? And I'm going to assume without loss of generality that, of course, A is less than or equal to B is less than or equal to C. Okay. In which case, what I'm trying to show is that the maximum of AX plus bx plus cx is less than or equal to b plus c. Okay, that is what is being attempted here. Okay, hopefully that seems quite reasonable, right? Because I'm trying to show that the sum of all these is less than or equal to, well, I'm sorry, not less than or equal to. The sum of all of these, if x is any point is on the interior or on the boundary of the triangle, this is a strict equality. So the maximum of ax plus bx plus cx equals b plus c. Okay, that's what we're trying to show. How are we going to do this? Well, I said I would present a classical proof first, and so here's what we're going to do. I'm going to draw a line here, a line segment here, that is parallel to CB. Okay, so I don't know. Let's call this PQ. And I do really like this proof. It's a fairly clever one. Okay, so call this line segment PQ. Then of course PQ is and it's drawn in a way so that PQ is parallel to CB. Excuse me. You want to draw PQ in a way where PQ is parallel to CB. Okay? All right. So PQ is parallel to CB. Now, we are going to sequentially apply the triangle inequality in various cases. So for example, first of all, you get that the quantity that we're examining is, of course, AX plus BX plus CX, right? First and foremost, note that BX is less than or equal to XQ plus QB by the triangle inequality applied to this triangle. So this BX is going to be less than or equal to XQ plus QB. And CX is going to be less than or equal to CP plus PX by applying the triangle inequality to this triangle. So doing both at the same time, we get that this is less than or equal to AX plus PX plus PC plus XQ plus QB. Now what I want you to notice is that XQ plus XP, like these two together, like this segment here. So XQ plus XP over here is just PQ, right? So this is just going to be PQ. So XP plus XQ is actually just going to be PQ. Okay. Does this actually help us that XP plus XQ is equal to PQ? Well, let's think about it. So basically we started with this sum, right? We started with this sum over here. Like we're adding these three segments, right? And what we've shown is that that is less than or equal to the sum of these segments. So there's this one, this one, this one, this one, this one. Okay? But now, remember, the triangle APQ is similar to the triangle the triangle AQP is similar to the triangle ABC. Okay? So the triangle AQP is similar to the triangle ABC. So if A is the longest side of ABC, that means PQ is the longest side, right? And if B is less than or equal to C here, that means, of course, that AP is going to be less than or equal to AQ. Because once again, these triangles are similar. So we know for a fact that AP is less than or equal to AQ. So that means that since AX is a Chevian of this triangle, then AX is going to be less than or equal to AQ. Okay? AX is going to be less than or equal to AQ by the fact that we showed earlier. So AX is in fact less than or equal to AQ. Oh, is it too dark or red? Okay. So now, after a lot of work, we managed to figure out that AX plus BX plus CX is less than or equal to AQ plus PC plus QB plus PQ. Let me just draw the segments that we're using here. So AQ is this one, QB is this one, and PC is this one, PQ is this one. Okay, so our starting sum AX plus BX plus CX is less than or equal to the sum of these red segments over here. But of course, AQ plus QB is just equal to AB. So, replace this with an AB. Huh, interesting. So now we have our starting sum, which is AX plus BX plus CX, right, is going to be less than or equal to AB plus PQ plus PC. But once again, because the triangle AQP is similar to the triangle ABC, and we know for a fact that A is less than or equal to B, that's going to mean that PQ is going to be less than or equal to AP. So we can replace PQ with AP. Because PQ is less than or equal to AP. But now, what is AP plus PC? AP plus PC is just AC. How nice is that? So this, AB plus AC, which is of course equal to B plus C, which is exactly what I wanted. So with incredibly clever uses of the triangle inequality, right, and other such shenanigans, you can give a classical, like ancient Greek geometry style proof of the fact that AX plus BX plus CX, its maximum value is never going to be larger than the sum of the largest two sides. And I really do love this because, like I said, it's a completely elementary proof. And it just follows from just simple repeated uses of the triangle inequality and triangle similarity as well. So I personally love this. I think it's a lovely proof, okay? But I mentioned to you earlier that there is something deeper going on here that I've been kind of alluding to. And to see the deeper thing that's going on here, I'm going to give a slightly more modern proof. I'm still only going to use elementary geometry facts, right? But the style is going to feel a little bit different. Okay, the style is going to feel a little bit different. Also, if any of you here have any questions about anything that I've done so far, please let me know. But now I'm going to give a slightly more modern proof of this statement. Okay. Extend AX to CB using the new location of X. We're done. No, I don't think the inequalities work out correctly, Ken. Let me think about what you're saying. So you're saying that all you need to do is, let's see. So you're saying all you have to do is extend AX here. So this is AX B C. using the new location of x. You might have to say a little bit more. I'm not sure how this exactly does it, because you're still stuck. Because, right, like, if you try to use the triangle inequality in this context, right, you would get, you know, ax plus bx plus cx is going to be less than or equal to, I guess, ax plus 2 copies of xy plus cy plus yb, right? X is now on cb. Well, once again, using completely elementary methods, how do you know that you've only made the sum larger by doing that, right? You're kind of using like a continuity convexity argument, which of course is exactly what I'm going to do now. But you don't, like, I don't know, if you were trying to tell a classical Greek geometer, right, or a middle schooler, they would not accept the logic without a proof that pushing x to cb would only make the sum larger, right? Unless you can give an elementary proof of that, then I guess you could do it using this tactic. You're not wrong though. Like, pushing this x over to cb will only make the sum larger, right? I totally agree with that point. I absolutely agree with that point. That pushing x to cb will only make the sum larger. However, we do need a proof of that fact, right? I don't think it's completely obvious by purely elementary means. Okay, so if you're just joining us, we gave a completely elementary proof that the maximum value of ax plus bx plus cx is equal to the sum of the larger two sides. When x moves as close to vertex A becomes 0 and the other two, B and C. You're right, again, Selesh, but how do you know that that movement only makes the sum larger, right? That's what you would have to prove. So how do you know the motion that you're doing doesn't accidentally make the sum smaller, right? I agree with you, like, you know, the idea, I think morally the idea that you're giving is correct, but you need to give some justification for why you're moving the point x closer to the boundary actually makes the sum larger instead of smaller. Hello, Iago. Okay, so in any case, I mean, I hope you'll agree that I previously gave a completely, you know, nothing hidden proof that the maximum value of ax plus bx plus cx is going to be the sum of the larger two sides. You know, a completely rigorous proof. But I want to give a second proof using a slightly more modern thought process, okay? Let's think it through. So, first and foremost, I want to make a claim, okay? Here's my claim. Let's say you have a line, like so, and let's say this is x1, and let's say this is x2, okay? I'm going to say that x0 is the midpoint of x1, x2. So let's say this point x0 is the midpoint of x1 and x2, okay? Now pick a random point P anywhere in space. So this is my point P. You can pick it anywhere in space that you like, all right? Now draw px1, px0, and px2, right? You have px1, px0, and px2. So here's my claim. Px0 is always going to be less than or equal to 1/2 of px1 plus px2, okay? And by the way, I'm essentially adding rigor to exactly what Ken and Selesh said earlier. Also, I'm writing over myself, so let me just move this over. Hopefully you can see that. So I'm essentially kind of rigorizing and like making more careful the precise arguments that were given before. Like, why is it that pushing x closer to the boundary makes the sum larger, right? That's exactly what we're thinking about right now. Well, proving something like this would take us a long way to justifying that. So why is it true that px0, so remember x0 is the midpoint of x1, x2. Okay, so x naught is the midpoint of x1 and x2. This is a simple one. Why is px naught less than or equal to the average of the length of px1 and px2? Hello, Brian. How are you? So once again, if you're just joining us, I gave an elementary proof of what this maximum value is going to be. Now I'm going to give kind of a fancier, like a more slick proof for what this maximum value is going to be. Okay. So px naught, what I would like to, so remember, x naught is the midpoint of x1 and x2. And what I would like to show is that px naught is less than or equal to 1/2 whatever the length of px1 and px2 is. Why would that be the case? Why would that be the case? Well, here's an idea. What you can do is you can take this exact diagram and rotate it 180 degrees. So imagine copying this, rotating it 180 degrees, and then pasting it. What would that look like? Well, I can kind of do that in Paint, but I've copied this, okay? Now imagine I rotate this 180 degrees and then paste it right at the bottom, okay? So it would look like this. Be another point. I'll call it P prime. And this extends down, okay? So, yes, thank you, Brad. So px naught, px1, px2, px naught. So what I did is I just copied this diagram, I rotated it 180 degrees, and I pasted it, okay? Now, you would all agree that p prime is just twice px naught, right? But we also know a couple of things. So p prime, right, by the triangle inequality is going to be less than or equal to px1 plus x1 p prime, right? Okay, this is applying just the triangle inequality to this triangle here, right? Hopefully you can see it. So p prime should be less than or equal to px1 plus x1 p prime, okay? Hopefully that seems reasonable, all right? But remember, p prime is just the double of px naught, so I can just write this. So this is 2 px naught, because p prime is just the double of px naught. Okay, wonderful, wonderful. So this is great. So this is px1 plus x1 p prime. But of course, because of the way I constructed this by copying and rotating 180 degrees, x1 p prime should be the same length as px2, right? This length down here should be the same length as this up here, right? So I can replace x1 p prime with px2 because of the copy paste construction, right? So I can replace this with a px2. Okay, fantastic. Now dividing both sides by 2 gives us the desired inequality over here, okay? So px naught, if x naught is the midpoint, is always going to be less than or equal to 1/2, or like the average of px1 plus px2, okay? Something very interesting I want you to note about this. First of all, when is this going to be... this is only going to be an equality if p is equal to either x1 or x2, right? Depending, okay? So think about that for a second, right? So if p is equal to x1, for example, right, then px1 is equal to 0, right? And px2 is just going to equal, you know, twice whatever px naught is, right? So the only way that this inequality can be an equality is if p is equal to one of the two endpoints, right? Otherwise, you get a strict px naught is less than, strictly less than 1/2 px1 plus px2. Okay? So, hopefully I'm not saying anything that's completely crazy to you guys, and you have this. Okay. Now here's what I'm going to do. I'm going to define a function, okay? I'm going to call the function s. So s of a point x, right, is just going to be the length of ax plus the length of bx plus the length of cx. Okay, so I'm now defining a function. So this is much more in line with what you guys were thinking about. I guess you're all modern mathematicians in the chat over here. But you define a function sx as ax plus bx plus cx. Okay, so you can imagine as you move x around, ax plus bx plus cx changes continuously. This is a continuous function, and this is what sx is. Okay, but here's what I want you to notice about this particular function. Based on what we just said, okay? Based on literally what we just said. Okay, let's say you have a triangle, ABC, right? And let's say you, inside this triangle, have x1, x2, with a midpoint x naught. Okay? You can compute ax naught plus bx naught plus cx naught. Right? You can also compute ax1 plus bx1 plus cx1. You can also compute ax2 plus bx2 plus cx2, right? This is just computing the value of sx at different values of x. So let me use some colors so what I'm doing is abundantly clear. So for example, sx1, for example, like sx1 would be the sum of these three lengths. Agreed? These three lengths in blue. Similarly, if I was interested in sx2, that would be the sum of these three lengths over here in yellow. Agreed? And if I was interested in sx0, that would be the sum of these three lengths in green. Maybe I'll pick a more distinctive color than green, because yellow and green could look kind of similar. So maybe I'll do pink. So if I'm interested in sx0, that would be the sum of these three lengths. Hopefully that makes sense. But based on this here, right, you know that this pink length over here, right, is less than or equal to the average of this blue length and this yellow length, which means the sum of the pink lengths is less than the average of, the sum of all the blue lengths and the sum of all the yellow lengths. In particular, what this is telling you is that this function is only going to it cannot attain its maximum value in the middle. It has to attain its maximum value at one of the endpoints of this line segment. Please, please, please let me know if there are any questions about this. Okay, so this is a more kind of advanced point of view, right? But the idea is that you define a function sx, right? Where you're adding ax plus bx plus cx for any chosen value of x, for any chosen point x. But then you notice that if you evaluate sx on an endpoint, you have this property, right? Where px0 is less than or equal to the average of px1 plus px2. Which of course tells me that sx0 must be less than or equal to one of sx1 or sx2, okay? This is very important. So whichever one is larger, right? So I'll write it down here. Sx naught must be less than or equal to, must indeed be less than or equal to 1 of Sx1 or Sx2, whichever is larger. Let me know if you see this. If you don't see this, take another look at this one again. So px naught is less than or equal to the average of px1 and px2. Let's say px2 were the larger. Let's say px2 were longer than px1. Then this would be less than or equal to px2 plus px2 over 2, which is just px2, right? So px naught is always going to be less than or equal to whichever of these two is larger, which means Sx naught is going to be less than or equal to whichever of these two is larger. Okay. Not necessarily. So for example, if let's say you had equality over here. Let's say px naught is 2 and px1 were 1 and px2 were 3. Right? Then this would be saying that like 2 equals 1 plus 3 over 2, essentially. So px naught is less than or equal to the average of two numbers, where equality is possible, depending on where the position of p is. But if px naught is the average of a collection of numbers, it must be less than or equal to the larger of those numbers, right? That's all I'm saying here, essentially. So let me know if that makes sense, Ken. Okay. So now what we've done here is something rather interesting. What we've done here is we've shown that if you have a triangle, right, and you evaluate ax plus bx plus cx on any kind of like line inside the triangle, on any line inside the triangle, the maximum must occur on the boundary of that line, okay? So you have a continuous function, right? And you can evaluate that continuous function on this entire line. You know the maximum has to occur on the boundary of this line, okay? But that means that the maximum of the function has to occur on the boundary of the triangle, right? So this kind of makes rigorous the stuff people were saying in chat earlier, right? So, for example, if you think the maximum occurs when when x is like over here, right? I can draw another little line here and say, well, actually, move it a little bit further, and in one of the two directions, it will get larger, okay? So essentially what I've shown is that the maximum of ax plus bx plus cx could never occur on any point in the interior of the triangle. Because if you try to make it occur on any point in the interior of the triangle, right, you can always push it a little bit on a line segment to make it a little bit larger, okay? So the maximum of ax plus bx plus cx cannot occur on the interior of the triangle, right? Or I'll say it more carefully. So the maximum of this function cannot occur in the interior, when x is in the interior of the triangle, right? When x is in the interior of the triangle. Happy you like it. And so now you can give the arguments you were giving earlier, where yeah, it is safe to move. You know it's safe to move around the point, and that will make the sum larger, okay, of the triangle. But there's more. So now you know that the maximum has to occur on the boundary of the triangle, and now it's very easy to check that the maximum will have to be the sum of the lengths of two sides. So for example, you know, you draw your triangle, okay? And let's say x is on the boundary of the triangle, so maybe x is down here. So this is, you know, this is A, this is B, this is C, this is X, right? So now AX plus BX plus CX is just equal to, well, AX plus BX is just equal to AB, right? So this is just CX plus AB. But remember, CX is going to be smaller than whichever of AC and BC are larger, right? So we're done, right? So the maximum of AX plus BX plus CX has to be less than or equal to the sum of the larger two sides of the triangle, okay? A fairly simple, fairly modern proof. But I want you to notice something about this proof. We've actually proven something much, much, much more powerful and much, much more interesting. I'm going to write it down. So, the maximum value of any convex function, and I'm continuous, right? The maximum value outside is larger, but I am insisting that x be in the interior, or like in the interior or on the boundary of the triangle. I do agree that if you plop x on the outside of the triangle, Iago, you'll get a larger value. But what I'm trying to say is that buried inside the proof of this very classical problem is this following much more modern, much more powerful fact, which is that the maximum value of any kind of like continuous convex function, right, on a convex domain occurs on the boundary of the domain. So that's really interesting that this very, very, very old, very, very classic problem contains inside it, I said on the plane, though, you know, you can actually extend this argument in higher dimensions as well. It's not that challenging. So yeah, so it really doesn't matter the shape as long as the function is convex and the domain is convex. So be careful. Be careful about that. So yeah, for real, you can actually extend this argument morally anyway to any situation where the function you're optimizing is convex and the domain you're optimizing over is also convex. Of course, everything I've done so far only applies in the plane, right? So actually, I mean, I will say you're all very smart because you noticed very quickly that when you move x closer to the boundary, it should be getting larger. But this is essentially what's going on here. This function, ax plus bx plus cx, is a convex function. Okay, well, that's all I've prepared for today. So I hope you guys enjoyed it. I hope you guys enjoyed both the kind of the classical proof of this fact and the kind of more modern insight that is contained inside it. So I'll be streaming again on Saturday at 1 p.m. with more fire mathematics. Hold on. So Ken says, can you just pick the center of mass of the shape and choose the point furthest from there? It would depend on the function that you are optimizing, right? I don't think there's a general theorem that would apply to any kind of convex function, right? Iago says on the sphere as well. Yeah, this theorem applies on, well, yeah, it applies on the sphere as well. Absolutely. A sphere is convex. And you'll find if you take a convex optimization class, a lot of the problems are happening on the sphere. All right. Thank you so much to everyone that showed up. I had a good time doing some 2,000-year-old geometry. And if you enjoyed it, I hope to see you again on Saturday. All right, then. Peace.